We're going to get started in just a minute. A couple little bits of housekeeping first of all. We have 3 speakers tonight talking about different aspects of 3D printing, after which we'll have some question time and then food and drink and a chance for more questions outside. As far as questions go, we take questions at BrisScience by paper. So on your way in, you would have received a slip of BrisScience question paper. At any time during the talks, you can write down your questions. We will come around and collect those afterwards, and then we'll ask as many of those as we can in the time that we have left. Otherwise, as I said, there's a chance to ask more questions afterwards. We also take questions over Twitter. So your phone, turn it on to silent, and then load up the Twitter application, #BrisScience. And we'll go through those as many as we can as well. Right. So without further ado, good evening, ladies and gentlemen, and welcome to BrisScience, proudly presented by the University of Queensland and hosted here at the fantastic Edge at the State Library of Queensland. I'm your MC for this evening, Joel Gilmore. Tonight, we are going to hear from 3 scientists who are pushing the forefronts of Star Trek replicator technology, otherwise known as 3D printing. Our hope tonight is that by the end of the evening, that we will change the way you think about manufacturing, about food, and about dentistry. And after that, you can sign up to use the 3D printer here at the Edge with some great training sessions. For now, though, I'd like to introduce our first speaker for this evening, Dr. Michael Bermingham. He's a mechanical and materials engineer at the Queensland Centre for Advanced Materials Processing and Manufacturing at the University of Queensland. He's working with new metallic additive manufacturing, or 3D printing, technologies that can enhance the design and manufacture of products for medical, automotive, and aerospace applications. He claims he's not trying to become the next Iron Man. I'm not absolutely sure I believe him, however. Could you please welcome Dr. Michael Bermingham?
Good evening, everyone. It's a pleasure to be here tonight to talk to you about 3D printing or additive manufacturing. So, you all have an interest in 3D printing. That's why you're here. You've heard the media headlines. Headlines such as this: 3D printing is a game changer. Perhaps it's the biggest game-changing technology since the internet, is what the media says. We're told that it's groundbreaking technology, that it's going to revolutionise manufacturing and perhaps be the next industrial revolution. And perhaps the most scientifically credible and influential of all headlines: Donald Trump thinks 3D printing is important. So there's lots of interest, lots of media speculation around the space. Tonight I'm going to give you a bit of an engineering introduction to 3D printing, what it is, and show you some applications. So 3D printing, or there's lots of names, additive manufacturing or rapid prototyping, is the process for fabricating a component by building it up from scratch, layer by layer. Now, 3D printing can be thought of a lot like 2D printing. It's just 2D printing over and over and over again. So most of us have a bit of a visualization of how a 2-dimensional paper printer works. So there's a bit of an image up there. So we have a print head that moves along a particular axis, and for argument's sake, I'm calling this the x-axis. And in doing that, it creates a line of ink. After that line is completed, the paper moves a small increment along the y-axis, and the print head moves back and deposits another layer of ink. Now, this repeats over and over again until an entire page is printed. Now, what if we change this a little? What if we added a 3rd dimension? And so instead of printing on just 2D, we would print one layer and then we would reprint on top of that layer again. And then what if we change the material? So we're not using ink, we're using polymers or metals or composites or whatever it might be. So this is the basis for 3D printing. And so 3D printing has come a long way in recent times. So here's a fairly simple video that I took on my phone. This is an entry-level printer, and you can see that it's moving. You can see an X and a Y movement here, and there's a build that's been on there for a little while. You won't actually see the Z step, the vertical step, because it's about 1/5 of a millimetre in this case, so your eyes won't notice that. But after it prints an entire two-dimensional profile, it then steps down in the Z direction, that small increment. So we hear a lot of 3D printing. There's a boom, supposed boom. So, but the reality is 3D printing's been around a long time. So the world's first printer was in the 80s, in 1984, and the reason that we're seeing hearing so much about 3D printing now is that technology is advancing. So take a 2D paper printer from the 80s. What would take minutes, perhaps minutes to print, now takes seconds. The same concept with 3D printing. So what would take days now can take minutes, perhaps. So there's a real advance in technology. And the other reason is that technology affordability. So here's an ad from an early 2D paper printer. Now you can't quite read it there, but this printer is priced from $700. So this is in 1984 and 85. So $700 is a lot, particularly in 80s currency. So I went to Officeworks website. This is a screen grab. $3. $3 for a printer. It's remarkable. So technology is becoming very cheap. What can 3D printing do? So this is about a year old, this story. So turtle gets 3D printed titanium jaw, now looks like supervillain. So what's happened here is some poor turtle's been hit by a boat and his jaw's been disfigured and certainly will die without human intervention. So what some people have done is that they've used a scanner, they've scanned the turtle and digitally created a new jaw for this turtle. And then they went to a 3D printer and basically, like Control-P, they've skipped a lot of steps and just produced this jaw. Now, I want you to think about this process just for a little bit. Think about what supervillains would have had to do before 3D printing. Now, for those that recognise this character, this is Jaws from the James Bond movies. Now, Jaws has steel teeth. Here he is chewing through a cable. Now, Jaws wasn't born with teeth. He was certainly born before 3D printing. Think about how he made those teeth. Someone had to make them for him. Now, I'm assuming that they were made by a casting process. This is where you melt liquid metal and you pour it into a mould. Dentists often still use this process. So I'm going to describe that process, and it's not really important you understand all the steps, but I want you to understand that there's a lot of steps and they can be expensive and time-consuming. So first of all, someone needs to make a pattern of the teeth, so a replica of the teeth, and they sculpt this out of wax, and they have to get it just right. And then they need to make a mould. It's like when you make ice cubes at home, you need to pour them into a mould, the water into a mould for it to set. The same concept here. But to make a mould, we take that wax pattern and we dip it in a ceramic slurry to form a coating. Imagine dipping your finger in paint. A thin layer of paint stays on your finger and it dries. Well, the same process here, except we dip that, once it's dried, we keep dipping it into the ceramic, getting it thicker and thicker and thicker until the mould is sufficiently strong enough. And then after that, we need to put it in a high temperature furnace, bake out the wax, burn the wax out, and sinter the ceramic particles together so they're nice and strong. Then we need to find a high temperature furnace capable of melting steel, so we're talking 1400 degrees Celsius. And then someone has to cast that and hope that there's no defects getting in there, because supervillains don't like defects like porosity, and they're not very friendly when, the lackeys go back to report defects. And then after that, someone has to break it out of the mould, do a lot of polishing, finishing operations we call, so grinding, sharpening the teeth, lots of steps. Now, I've described a lot of steps there, and I think you can all understand that there's a lot of work goes into that. Now, the power of printing with this turtle, the modern day supervillain, has gone from a digital file to an actual part by skipping all those steps. That is what is interesting about 3D printing. Now, engineers get excited about 3D printing because it allows us to enhance our designs. So here's an aircraft. I work in working with aircraft producers, And typically components are machined. So this is a subtractive manufacturing process where you basically start with a big block of metal like this, and then you use a cutting tool to physically cut out the shape that you like. And it's a very wasteful process. And in aerospace, we talk bite-to-fly ratios, and this is simply the ratio of material that you start with. So you might buy 20 kilograms, and then you turn 19 kilograms into swarf, into scrap chips, you throw that in the bin, and you're left with 1 kilo that goes on the actual aircraft. So it's very inefficient and wasteful. And engineers need to design the components like this so that they can be manufactured. If you can't manufacture it, it's a useless part. And so we need to allow for our cutting tools to be able to get in there. So you'll notice there's deep pockets where a cutting tool can get in there and remove material. Now with 3D printing, we no longer use tools. So we're free to design our parts. And so engineers are coming up with new ways to design these parts. So with 3D printing, we can have hollow parts that have sort of bamboo structures. Now they're just as strong, but they're a lot more shape efficient. There's a lot less material there, so they're lighter, and they can only be manufactured by 3D printing. So here's an example. This is off the A350 new Airbus jet flying around. So on the left here we have the conventional bracket. Now these are little brackets, but they all add up. And on the right we have the new design that's designed specifically for 3D printing. And in doing so, around 50% of the weight has been removed, and we've saved 90% in material, up to 90% in material costs and efficiency, less energy to make it. So it's a pretty powerful tool. Now the main thing with 3D printing, from an engineering perspective, is that complexity is free. When you design components, you can design them to be very complex. Here's some photographs from, I'm part of a research group, I'm part of a research group that does a lot of 3D printing down in Melbourne, and these are some of the components. They are, done it again. Look at this structure. It's a hollow lattice type of structure. It's very strong for its weight. You can't make that any other way except for 3D printing. Now, 3D printing also has a role in conventional manufacturing industry. So I've done some work with White Industry, which is a foundry. So they do a lot of that casting. The process that I described for making Jaws teeth, they do it. Now, this is an impeller. This is an impeller, this is a part. Now they wanted to know, they don't want to 3D print the impeller. What they want to know is, can we 3D print the mould so that we can make the impeller? So they've identified all those steps I described with Jaws. They're expensive and time consuming, and they said, can we just skip them and print it? So we thought, why not? So the first thing we needed to do is capture a digital model of our part. And so we used a scanner at UQ to do that. And then we captured our digital file. And then from this, we need to make a mould. So we make a mould from that model and design it for casting. So there's certain features in a mould. For example, you need to have a hole to pour the liquid metal into. And then you need to have little runners. That's not important. But after this, after the optimization, we sent this to the sand printer. So this is in 3D printing sand moulds. And there's a picture of the moulds. And then after that, they get sent back to the foundry. So the important step here is there's no manual work in this. The printer does it all. And then the casting is made. And then after that, we need to break the mould, and we have our final part. And so that was a nice one. Now, another project we've done is in metal printing for Volvo trucks based here in Brisbane. They're making rural firefighting vehicles, bush firefighting vehicles. And so they're doing that. We all know Volvo. They have a huge commercial truck and automobile business. And so they have this particular truck that they were retrofitting for rural firefighting. Low numbers, low productions. And one of the features is it has this plastic door handle. Now, plastic's no good in a bushfire because it melts for obvious reasons, so they wanted to make this out of metal. Now, we're talking low productions. Now, you could make this door handle a number of ways. You could machine it, you could forge it, you could cast it. But all those processes take time, and there are a lot of setup just to get a small number of parts. But what we've done is we used a metal 3D printing technology and produced it in a very short period of time. Another company we're working with is Cook Medical. Now, Cook Medical are based here in Brisbane, and they're the largest manufacturer of fully customised endovascular stents in the world, which is a great claim for Queensland. And so Cook are designing, I don't have time to talk about it, but Cook are designing products to treat aneurysms, aortic aneurysms. Now, if you have an aneurysm that's severe, you've got a few options. One is open heart surgery. Two is EVAR, which is the process Cook uses, non-invasive endovascular repair. And the third is you just do nothing and you probably die. So the preferred option is the second one, and that is where we take a small incision in the groin and they insert a stent using a device like this up to the affected area, and then they deploy it, and it basically becomes an artificial aorta, artificial vessel. And so Cook aren't actually 3D printing those devices, but what they are printing is patient anatomies to test those devices, because every person is different. And so they have a range of printers that they use, and so they'll print out their models that are taken from the medical scans, and then they will test to make sure that the solution is the correct one. But they also use them for a number of jigs and fixtures and prototyping. So I think I'm out of time, but I just want you to take the main message from this, is that 3D printing is great for prototyping and making small production numbers, and or where there's no other way of manufacturing that product, where 3D printing is the only way to do it, so therefore we can fully utilise clever design. So I'll hand over to our next speaker. Thank you very much.
Thanks, Michael. Fantastic stuff. We'll have some opportunities for questions shortly. Our next speaker is Professor Bhesh Bhandari, who is a food scientist at the University of Queensland, exploring the potential application of 3D printing for novel food production, design and development. Bhesh and his team are looking at how food can be digitally designed, printed in a three-dimensional shape and applied to develop new texture, taste and appearances. So tuck your napkins in and please welcome Professor Bhesh Bhandari.
Thank you very much, and good evening to everyone. Our previous speaker, Michael, presented printed material which we cannot eat. Now I'll present something we can eat. So this one is to develop, this 3D printing has given opportunity in food area as well to develop new food design, new food structure. As for example, mostly the 3D came through polymer science. You can buy, you can get very easily this sort of polymer 3D printer commercially. But food printers are not still available, but you can see that 3D printer food can print like cookies or biscuits or any other shape. As previous speaker mentioned, that what is the difference between 2D printer or 3D printer? Like normal printer, what we do is in the 2 dimension, like it can go length and width. But 3D printer allows to go to the 3rd dimension. So you can increase the height. Otherwise, you could have done only 2 dimension. So you can deposit layer by layer and then grow towards the height. So you can create any food which is higher than any food which is higher than the length and width. So you can do in the 3 dimension. So that's principle we apply in the food. So you can create this sort of food by 3D printing. Can you imagine that you can make burger You can make pizzas. You can make different shape of chocolate, pasta, even carrot. This made out of carrot, in fact. This made out of carrot. But you can eat very easily. It's soft carrot. The principle here is that instead of ink, what you use in normal printer, you use the food. They are the food material. You can have different type of food. You can have two extruder or the syringe, which can deposit the food. You can see that it's depositing towards the height as well, the dimension. So you can have two syringes, so it can deposit two types of food together. And keep in mind that the food, when you deposit, it has to be liquid. As soon as it is deposited there, it has to be solid. It has to solidify because it has to support its structure. Because what happens is, in the beginning it's liquid. When it comes to layer by layer, then it can't support its own structure. So whenever it deposits down, that has to convert to some kind of solid structure. So that's the big challenge, that how can you support that structure. In terms of the 3D printing, this is the fastest growing technology now. When we look at the recent publication in the Forbes, in 2014, the industry, 3D industry was about under 5 billion. Now, by 2020, it is going to be more than 20 billion. So in fact, it is growing so fast that it is really surpassing the previous forecast. It's doubling the forecast. So it's really growing very, very fast. So in the beginning, like as it was mentioned before, that the 3D printing started in 1984. Here I have said 1986, which is close to 1984. So from 1986 to 2011 until this time, it was more limited to product design and prototyping. Now it has gone to end product production since 2014, and it is expanding to food production and hospitality industry as well. So this is very recent in food area. So why we need to print the food? What is the benefit of doing it? Because it's a new digital generation needs digitally designed food. They don't like handmade or anything, dad, mom prepares. They want something to be printed. So, and this gives the opportunity to develop new texture and taste as well. And you can design a food, you can design in the computer, and it can be made at home, or it could be commercially manufactured. So same design you can make at home if you have a printer, or it can be commercially manufactured. You can have database, or you can go to the Google and then certain shape of the food, you can print it straight away if you have a printer at home. And also, it gives the opportunity that you can make personalized food for different age group, elderly people, or children, or adolescents. They have got different demands, different type of food, different type of texture. And also, it can provide some sort of new type of nutritional profile in the food, and develop new taste you can develop new taste as well. In terms of the evolution of food printing, as I told you, this is very recent development in food area. So until 2014, it was focused on shaping of the food, creating different shapes, like pasta shape or chocolate, It was just focusing on that one. And now, it is more going through the personalized recipes, like making carrot out of the carrot, and creating different texture of the food, so they are palatable, they can easily, consumable, and also they are attractive as well. And you can have a personalized food. I want this type of food having this sort of nutrient content, so you can print it accordingly. And now it's developing so fast since 2014 that almost everybody is working in 3D printing all over the world in food. You can see even Philips, Electrolux, all those companies, Barilla, they are making 3D printers for food. It's not in the market yet. They can't really challenge, they can't take the guarantee because it's very complicated. Food is very complicated. I'm going to mention later. But there are different companies, big companies are starting making trying to develop the food printers. And also different research institute like Cornell University or like Griffith Institute in New Zealand, or even some companies like Nestle and Mondelez, they are trying to print the food, design new type of food and print them. And we have started working since 2015 in University of Queensland. So this is very recent in our university as well. So food is not that easy to print because food is different. So every food is different. So you can't print it straight away. So you must have some knowledge on the food, that it is printable. You need to do all these. You must have some knowledge on the melting property of the food, gelation property of the food, cross-linking, glass transition, powder properties. All these properties are essential to know when you are printing food. So it's not that easy. And when you buy a printer, it may print one type of food, but it may not print other type of food. So we have to work out how you control the property of the food so that it is printable. Because as I told you that it can be printed, it can be deposited, but it doesn't support its structure. It just becomes a mess. So it's not that easy. So it's really the task of the food scientist. Printer is easy. People can make fruit printer. But the thing is, as soon as you try to print, it doesn't print. It prints, but it doesn't remain as a shape what you want. So really, there is a role of the food scientist like us. So what we do is we don't develop the printer. We look at the food property, like we control the food property so that it can be printed in a form that we want. So there are different forms of the food which can be printed. It could be in liquid form, powder form, or some sort of bioprinting as well. That's not really in our area, but these are the foods that can be printed. In the liquid form, like you can have extrusion type of printer where we use something which can melt like chocolate, and we can extrude layer by layer. And as soon as you make a layer, it has to set so that you can put another layer. Otherwise, it will just flow around, so it doesn't support its structure. Same thing you can do in the inkjet printing, using the inkjet printing technology. You can have a supportive structure because if that product cannot support, then you can deposit the whatever thing you want to print. It looks like a mold, but that mold can be printed as well. That mold can be edible. That can be edible, so we can put another edible thing over here. So both are edible, so you can print using this sort of technology. The other one is using the soft materials like a pasty type of consistency. You can make pasta. You can make some sort of surimi product like that shape. Chocolate, as I gave you, chocolate is you can melt and then deposit. And you can use the inkjet one. You can see before I just told you that you can make this sort of edible type of thing, and there are different wells. You can deposit other type of product. For the pizza, you can print that pizza base and the pizza sauce or tomato sauce. And then even in the donut, you can print anything topping, icing topping or whatever you want to print. Another form is you can use the powder of the food. Powder means mostly used in the confectionery, like a sugar powder or something to make the confectionery product. You can use laser or some sort of liquid binder. So laser is very precise, so you can really make any type of shape. You can design, and it can direct the beam to any shape and then melt the powder and create that shape. So layer by layer. So you print it, put another layer of the powder, and then prints automatically. You don't have to do anything manually. So at the end, you can get this sort of shape. Either you use laser or you can precisely use very fine liquid binder, and you can create that sort of shape as well. You can see that sort of complex structure of the confection you can make out of these powders. So you can see this done in a very complex structure, very complex chocolate structure, and that's another using the sugar. So this cannot be made by any means other than 3D printing. So another application is bioprinting, which is not our area actually, but you can see that people have tried to use making the artificial meat. You can print the suspension onto the agarose rod that gives some supportive structure as well as some sort of nutrient as well. And then you can create 3D construct, remove that supportive structure because it's already bound, and then you mature and you get the 3D printed meat. And there is already a patent here. So it's a bioprinting. And now it's so fast developing that we scanned the patents, how many patents are there around the globe. So we found out that there are liquid-based printers, there are 64 patents. And the powder-based print, there are 16 patents, and bioprinting, what I just presented, there is 1 patent. So by the end of December, that many numbers were recorded. But by now, I think I'm not surprised if they are double the number of patents already filed. And you know that in China, most of the work is done in China because they have got even the 3D printer you can buy in China very quickly, and they're developing very fast. So most of the patents are registered in China. Now, coming back to the food structure design, as I told you that it can create any shape, and you can make personalized mold, and also you can create some sort of microstructural design, layer by layer design of the food. The advantage of layer by layer design is that you can produce low salt, low fat, texturized food by doing that. As for example, if you want to produce low salt food, you don't have to salt everything. You just one layer, very thin layer, you can make a layer of the salt. You want some perception of the salt. The rest may not have salt. So it will go to the tongue and you will feel that it's salty, but not necessarily everything is salty. Same thing, you can put layer of the fat over here. You don't have to put fat all over the food. So that lubrication property, it's given by some single layer of the fat. And also that can create a texture which can be soft or crisp or anything you want, or flexible or anything you want by just manipulating the texture of the different layers. So it's possible to develop new type of food. Even you can introduce some sort of nutrient internally within the food. You can do anything. It gives the opportunity of developing a lot of food products. Just giving example, you can design this sort of 3D design in your computer. And then this has got layer by layer design. And then that layer design, in fact, outside looks layer. Inside, you can create the hole. You can have the gap inside. You can create anything, any type of thing, which is not possible to produce by yourself. It can be done, it can be printed by 3D printer, but it does from bottom to top, layer. So you can have any gap or anything. Even I saw some presentation that you can print a man, with everything, intestine and everything, really built perfectly because it prints from the bottom to top, layer by layer. You can do. Same thing you can do with the food as well. So this is the digital food for digital generation. So you can see that our children, I don't have grandchildren yet, but they start with iPad. They can design or they can import the food design, and then they can take a picture of any food, 3D design of the food, and then they can print it in the printer at home. So they can eat that. You don't have to force them because they print it by themselves. The other thing is that elderly population is growing across the world very fast. And then if, we know that elderly population has got, many elderly population has got problem of the chewing or swallowing. So you need to modify the texture of the food so that they can eat. And they have to continue their enjoyable life, enjoyable eating habit. So we need to develop food for the elderly, and this gives very good opportunity to create new food, very attractive, very appealing, and very soft, so that elderly population can eat. So you can see how attractive the food are. They're all 3D printed food. So that's the future food. Even I'm preparing myself. So now I'll just show you how it works. That's the video taken in our lab, very simple one. So that just I'll show you the video. I hope it works. Sorry. This chocolate printing. So it is doing layer by layer. It is a love shape. And you can do some sort of dough formulation. You can put the dough at the top, and then it prints whatever you want, whatever shape you want, whatever you design, whatever. It's a pretty simple principle, in fact. Okay, at the end, I would like to acknowledge MLA who put part of the funding. I didn't put anything on meat, but you can see that they funded part of our project. Thank you very much.
Thank you very much, Bhesh. Good. Well, now that we've got you all salivating, we'd like to introduce our final speaker, who is Professor Saso Ivanovski, who's a periodontist from Griffith University. Using 3D bioprinting, Saso and his team are revolutionising regenerative medicine by printing living bones, gums and teeth from the patient's own cells. This research has big implications for the field because it provides innovative ways to restore form, function and aesthetics following the loss of tissue or organs due to disease or trauma. So please put your hands together and say "ah" for Professor Saso Ivanovski.
Well, thanks for that introduction, Joel, and good evening, everyone. So tonight I'll be speaking to you about bioprinting. So what better way to start than to consider what bioprinting is? And it's essentially three-dimensional printing of living constructs using layer-by-layer deposition of actual living cells. So how is this different from conventional printing? So this is, I have to thank Michael here because he actually gave a very nice introduction here of our supervillain turtle with its prosthesis. Well, there was excellent use of conventional 3D printing. The difference between that and bioprinting is that what comes out of the bioprinter is a living tissue. So the idea would be for that particular construct to be implanted into a patient and over time be fully incorporated into that patient so that by the time the scaffold material is resolved, the final result is that you cannot differentiate the new tissue from the patient's native tissue. So how is this useful in terms of regenerative medicine and regenerative dentistry? Well, again, Michael has talked about this before, and it's all about this concept of this new industrial convergence, okay? So great, exciting innovation in various aspects of technology, combining together to offer great outcomes for our patients. So medical imaging, there's been great developments in medical imaging and also in computer-assisted design. This can be combined with additive manufacturing and 3D printing. This is where the bioprinting comes in. And also with new techniques in medicine and surgery. And what we ultimately want to achieve is to create this personalized tissue engineering. So personalized is fairly self-explanatory, right? So personalized, something designed for a particular individual for specifically to address the issue or the problem of that individual. But what about tissue engineering? What is tissue engineering? Well, my 6-year-old son might consider this to be tissue engineering. But of course, this is not what we're talking about in the context of dentistry and medicine. What is tissue engineering? Essentially fabrication of body components outside in the laboratory, outside the body for implantation into the body. And there is usually three major components of tissue engineering. So we're talking about cells, the appropriate cells that can be instructed to go down a particular pathway. So usually things like progenitor cells and stem cells. That's why stem cells are so popular in the field of regenerative medicine, because they are immature and they can be instructed to go down any particular way that we want to manipulate them. And appropriate scaffold is absolutely essential, and then you need the right signals to be able to tell the cells what to do. And this ultimately results in these human replacement parts. And you know, these constructs now have been used in a variety of medical applications. So we've got attempts to make organs, connective tissues, and of course dentistry, which is my focus, as that is my field. I have to say, however, that the promise of tissue engineering has not yet been realized. I mean, we still do not have widespread utilization of tissue engineering for our patients. Possible exception maybe being some skin products or the odd cartilage product. There's a few little things here and there, but the huge promise that was there 20 years ago has not materialized. So now let's think about 3D bioprinting and how that might be able to enhance and bring forward our tissue engineering. So 3D bioprinting, essentially, it's an enabling tool. It's something that enhances what we are already trying to do with tissue engineering, but it is really quite a revolutionary tool at our disposal now. So what can it do? So you are able to deliver the cells. You have to deliver them in a bioink, of course, in a layer by layer structure, a three-dimensional structure, but you can also combine it with other materials. So the unique thing about the bioprinters is, of course, they've got multiple cartridges and nozzles, so they can actually deliver a variety of both cells, instructive materials, and even the scaffolds, all together programmed to precisely replicate a particular tissue. So spatial and temporal control is very, very important. It's a feature of the bioprinter, where you need to create constructs, organs with very careful control of when and where you deliver your cells and your materials. That's where bioprinting really comes into its own. It does still have the precision of a lot of the 3D printers. It certainly can do things at the micro scale, and we're now getting to the stage where we can even start to do things at the nanoscale. And in terms of delivery of instructive molecules, it can even do that at picoliter levels, okay? So it's 1/1000th of a liter. So these are some of the precision and some of the three-dimensional structures, just demonstrating that you can make multiple phases of different tissues using the bioprinter. So how might this be now used in dentistry or medicine? We do have some challenges in dentistry where we lose tissue or we are missing tissue, and one is certainly bone, right? So something as simple as losing a tooth usually results in significant bone loss. So you can really see here what happens, I'll come to this in a minute, what happens when we lose just a single tooth. Because the bone and the structures that keep the tooth in place are only really there for that purpose. They're there just to keep the tooth in the person's head, essentially, or jawbone. Once you lose the tooth, the bone becomes redundant, and the body is great at eliminating redundancy. So the bone gets lost. It gets remodeled or resorbed. And you can see here, the more teeth you have lost, the more bone you tend to lose. And over time, you tend to get a lot of resorption, and this can result in quite big changes to the facial structures. Very much looks like it ages one quite considerably if they lose their teeth and subsequently the bone that's lost as a result. So obviously this can be a major issue for patients, and everyone always tries to look for reconstructions to replace their teeth. But in order to replace the teeth, you need prosthesis, and to hold the prosthesis in place, you need bone. So lack of bone is certainly a big issue in dentistry. And even aside from tooth loss, you've got trauma and you've got pathology which can lead to significant loss of bone. You can certainly see here a major tumor requiring resection of the jaw, and this is almost impossible to recreate with currently available technologies, especially in an appropriate, predictable, long-term solution that gives the patient anything resembling close to their original function. So we do have some options. Of course, we've been trying to treat these patients over time. We've got ways of doing it. They're just not particularly good. And one of the most predictable or the classic way of treating these bone deficiencies is using autogenous bone grafts, and that means it's something that comes from the patient themselves. So you take a piece of bone from one part of the patient and transplant it to another place. And depending on how much you need, the source will vary. So if you need a small amount, you can go to another part of the jaw and just transplant it across. Not so bad, still quite painful, but not so bad. If you need a big part of bone, you usually have to go to the hip or the skull to do that. Obviously, that's got its own disadvantages. It's a major morbidity for the patient, a very painful procedure for the patient. And often, the results are still less than ideal. So the idea of tissue engineering with our bioprinted scaffolds would be to make custom-made scaffolds for the particular defect that we're dealing with using computer-assisted design. We would then create the scaffolds, print them, implant them, and they would be fully incorporated into the jawbone. So that's the principle that we're working towards. And we have some initial work along these lines, and here we can see a proof of principle scaffold that we've designed for augmentation, for vertical augmentation of bones. So what you can see here is a scaffold that can also, at the same time as delivering this bone construct, have a recipient site or a hole for the dental implant itself that will subsequently then support the tooth. And it's designed so that it can be implanted into the existing bone. So this is the intra-bony component that goes into existing bone, and this is the supra-bony or vertical augmentation component that goes outside. That's the stuff we are augmenting. And we can load that with our bioprinter, can load it with our hydrogels and our cells, and with an instructive osteogenic material, a growth factor that creates bone, a bone morphogenetic protein. Some of you may be aware of the concept. That's very, very osteogenic material that can make cells differentiate into bone-forming cells and create mineralized bone. And then here we can also place our implant into the hole that we've already created to receive this particular dental implant. So then the whole construct is implanted into the jawbone. You can see we can get very nice adaptation and increase in height of the available bone. And as this gets incorporated into the jawbone, you also have your dental implant there integrating with this new bone. So that's then ready to receive a prosthesis, a dental prosthesis. So not only have you got bone regeneration, but you've also got your implant all ready to receive a tooth. So the way this would work, again, just to summarize, would be a CT scan, a cone beam scan. It's very commonly utilized in dentistry to get a three-dimensional picture, digital picture of the jaw and the missing part. Using computer-aided design, we would then make our construct to replace the missing bone. Then our bioprinter, this data would be sent to the bioprinter. The bioprinter will precisely replicate our designed structure, and then we would surgically insert it into the jawbone. Now, the second and probably even more interesting application that we have for our 3D bioprinting, and this particular application is very much suited to 3D bioprinting, is the treatment of gum disease or the regeneration of gum tissues following gum disease. So this is, sorry, a little bit of a gory slide. So I'm glad we didn't serve dinner beforehand, but I'm not sure it's going to be very appetizing for dinner afterwards either. So this gum disease is essentially a disease which is caused by bacteria that accumulate along along the margins of the teeth and on the teeth themselves, and they result in a lot of loss of bone and structures that keep the teeth in place. Okay, so you can see big bone defects that result around the teeth, and it's very common. This is actually a very, very common disease. For people over the age of 45, probably 50% will have some form of gum disease, and 10 to 15% would have severe forms that could result in tooth loss. And that's exactly what happens with these sort of situations. That if it's untreated, the structures around the tooth, or the bone that keeps the tooth in place and the ligament, get broken down, and over time tooth gets loose and falls out. So even with treatment, we can arrest the disease, so we can remove all the causative factor, which is the bacteria around the teeth, but ultimately, even once we clean all it up and we arrest the disease, we cannot get the structures back. So people are left with this unsightly teeth appearance that doesn't look very nice, and also it's functionally not very good. And you've still got loose teeth, you can't function quite as well. So that's why we really need to try to regenerate these periodontal structures. But we can't do that with the available techniques. It does not spontaneously occur. It's very difficult to achieve because the tissue, even though it's in a confined area, you're thinking gum, how complex could it be? It's actually very, very complex structure. It's got the bone and the periodontal ligament, or ligament that runs between the bone, and then you also have this mineralized tissue, which is called cementum, on the tooth surface itself. So you've got these three structures, two hard tissues and one soft tissue, that keep the tooth in place. And to recreate this is quite difficult. And it does not occur with any of the procedures that we currently have. And believe me, we've been trying. So this is now where tissue engineering comes in, okay? So the idea of being able to try and control this process, this interaction between the different tissues outside the body in order to implant them into the body. So you would start with a framework, your cells, your engineered matrix, and implant that next to a tooth. So here you have your tooth surface, your engineered matrix that will then recreate this lost bone and attachment to the tooth, and you start to get your appearance and function back. But of course, it's not as simple as this. It's actually quite complex, because this is not a uniform structure. The structure's got bone, it's got ligament, it's got cementum on the surface of the tooth. And don't forget, these structures themselves have got blood vessels and nerves running through them. It's difficult to engineer without precisely controlling the spatial and temporal expression and deposition of the cells. And this is where bioprinting comes in. So we can print these multiphasic scaffolds with different components of ligament and bone and cementum, and try to incorporate cells into this so that we can recreate these quite complex structures. So this is the same concept that I showed you with the jaw. It's again scanning the defect, creating the scaffold, but the bioprinter allows us for printing of the carrier, scaffold, and the different types of cells in a very controlled and precise fashion that can only really be achieved by getting that level of sophistication that the 3D bioprinter can achieve. I must also emphasize here that all of these 3D printing applications that we have, and it's not just us, but almost worldwide, are really only at the preclinical stages now, so they have not moved to the clinical stage, but they are showing some significant promise in being able to move tissue engineering into clinical applications. So finally, before I finish up, I just want to share some thoughts about where I think this 3D printing or 3D bioprinting will move in the future, and this is probably somewhere down the road, but it's a concept of printing bedside or for dentists chairside. Okay, so you would have your printer being able to recreate and to treat defects immediately on the patient at the point of healthcare delivery. So be it the dental chair or at the surgery, but the printer would be scanning and printing your construct directly onto the patient. So with that, with those thoughts, I'm pretty sure now I've run out of time, and thank you for your attention. Oh.
Thank you very much, Saso. I'm going to invite the other speakers up onto stage. We'll now take your questions. So if you have a question slip, please wave it around and the BrisScience team will come around and collect those questions. While you're doing that, a couple of bits of housekeeping. Next month we are back on the 4th of July and we are asking, is science any use for saving species and habitats? So we're going to be looking at the value of monitoring and information and what that can really do or not for achieving nature conservation outcomes. So it should be a very exciting talk, so come along to that. We also have tonight, who went on the tour before the talk tonight? Right, who's going on the tour after this? All right, so if you're going on tour afterwards, Daniel with the red shirt will be just outside. Go and see him. He'll take down there. If you didn't sign up but you really want to go, there might be 1 or 2 places left. So again, check out Daniel at the entrance just at the end of the talk. Thank you. All right. Sorry, actually, one more bit of housekeeping. On the 3D printing, there is a 3D printer downstairs at the edge where if you take a training session, you can learn how to use it and then use it to your heart's content. Tonight, we're very pleased to offer 2 people a complimentary training course. And if you'd like to go on it, you need to find the lucky 3D printer token under your seat. So, 2 people, hopefully, under their seat will have a token. If it's not under your seat, you should check the seat beside you just to be safe. Or the seat in front of you if there's an empty seat. It's taped to the underside of your seat. Hey, we have a winner over there, and we have a winner there. Give them a big round of applause. I'll get you guys to come up here at the end of the talk, and I'll take your details, and we'll sort out how you sign up. So congratulations, and thank you to The Edge for teeing that up for us tonight. All right, questions. First question, I guess, is for the whole panel, is how big can objects be 3D printed? And maybe, Michael, will we be 3D printing houses?
Oh, it's already happening.
Yeah.
In
okay,
China.
next.
But,
Michael, you probably, sorry, people.
Yeah, so,
but that's, you don't print whole house, you print bits and bits and then you have to assemble them, isn't it?
Well, there are extrusion-based 3D printers in China that are fabricating houses. Again, there's lots of media headlines on that. They're sort of suited to emergency relief situations. Think about, what do we put in concrete? We put steel in concrete to give it structural strength. So there are some limitations. They're not printing with concrete embedded at this point. I'm not saying that won't happen in the future, but the ones that we're seeing are really just for low-cost, rapid production of houses. In terms of engineering structural components, there are metal titanium-based 3D printers that are fabricating parts up to 5 meters long. So these are very big aerospace parts. They're emerging. There's a few commercial machines emerging in the States based on that technology. And I will just add that those machines don't come out completely finished. The part doesn't come out completely finished. There's always a little bit of finishing required. We call it finish machining. So I showed you a picture of a component that had been machined. You will still make a similar component, but you do most of it by 3D printing. So you remove the need to completely machine from a solid cube, but you still have a little bit of machining to get the correct tolerances and make it as accurate as possible as it needs to be.
Okay, I've got a broad question. Will 3D printing ever evolve to be suitable for volume or mass production rather than just prototyping or low-volume custom parts? I guess this could go for food or manufacturing.
Yes, when there's a cost advantage to do so, absolutely. That said, it really needs to be a niche sort of product that has an advantage that can't be built in through a traditional process. So with manufacturing, you've got to think you have a lot of setup costs. So let's talk about forging. Forging's a process like blacksmiths, when they make swords, they hit it with a hammer, that's a tool. It's a very simple forging process, but we have big, complex machines that can do that. But you have to make a serious investment in capital in terms of making the dies. And so if you're making a small production run of perhaps 1,000 parts, it's just not economical to do that. But if you're making 1 million parts, then the cost of investing in these dies may be worth it. So look, there are some cases. There's an example where there's a couple of Australian guys who developed or designed a new beehive. It's called Flowhive. You can Google this at home. And so they're actually using 3D printing as a manufacturing process for their hive. And as far as I know, that's the core manufacturing process for critical components in that Flowhive. So it is being used in that way.
I think in medicine, it's without doubt, it's very suited to bioprinting or even without necessarily having cells incorporated into the construct. High throughput printing for medicine is very applicable because, I mean, medicine is very, very expensive regardless. So it's not like engineering where you've got cheap ways, other ways of making these constructs. There is really no other option. So anything that can automate processes and make them less labour intensive, I guess, would be useful. And off-the-shelf products that are 3D printed are to some extent already available in medicine, but I see that as being a very much a growth area.
Okay.
In food production area, I mean, this is the question that any people can ask always. These are new developments, but it is possible to have commercial production because, as I showed you, that you can have a number of injectors or depositors, thousands in fact, and then you can produce thousands of small product like cookies or biscuits or that sort of thing. So it is quite possible, but it's still a long way to go, technologically, because it's very, very new in this field.
We've got a question, which was, sorry, I have just lost it. I'll come back to that one in a moment. Okay, question for Saso from Adrian. How do you control contamination in bioprinting from disease bacteria?
Good question. There's a thing called GMP. You might have heard that, and that's good manufacturing processes, and it's pretty much a guideline or legislation that dictates how you will treat any biological product that is going to go into a human being. So that means that you have to work in what's called a clean room. So the environment has to be absolutely clean. There's multiple filters. There's negative pressure within the room, which prevents bacteria from going inside. There's anti-rooms where you come in, you get dressed into your sterile gear, you then go into your clean room. So those are very well-defined parameters, and we're actually working on that at Griffith. We have a basic clean room where we have placed our 3D printer. It wouldn't probably fulfill requirements for implantation into humans, but certainly gives us quite a clean environment for our preclinical studies.
Right. All right, a couple more questions before we break. Phil of Aquariums to Go asks, I make custom aquariums. Can a clear box be printed in large sizes and different shapes? I don't know, Michael, if you have any insights into, can you print clear?
You can print a number of polymers. There seems to be becoming more and more and more that are emerging. So while I can't specifically think of a particular one off the top of my head, I'm quite confident that you could do that. And as to printing complex shapes, then absolutely, definitely, that's what it's all about. So don't think about squares, think about something exciting and you know, gives it an advantage for using the 3D printing process to start with.
All right, second last question. This is a broad question for the panel. How many different types of 3D printers will we need to have at home? Polymer, food, metal, concrete, teeth? This is from Philip off Twitter.
Well, you know, you can have printers that can do more, that are what we call multiphasic, or they will have multiple cartridges so that you can apply or you can load each cartridge with the particular material that you want to print. So maybe one printer that's versatile enough to do many different materials. So polymers, gels, all those sort of things.
Yeah.
I think the possibility of having a full printer is very high because, you know, like that's quite easy and then it's quite applicable as well. So I hope in next 10, 20 years time it will be like microwave that everyone has got a food printer.
Right. Okay, my last question. This one is straight from me. Bhesh, where can I get me one of the chocolate printers?
I can give you the supplier's name, but it will cost dear. You know, it's very expensive at this moment. Yeah.
I'm getting pretty committed here. That's great. Ladies and gentlemen, could you please join me in thanking our fantastic panel this evening? We have some small...
Thank you.
It's fantastic to really be on the cutting edge of science. Could our winners please come up and see me? I'll get your details. Everyone else, please join us for, sadly, not 3D printed food, and we'll see you back next month. Thank you very much, UQ, for tonight. Good night.